Do you remember the massive global panic over the ozone hole?
Oh, wow. Yeah.
Right. Seriously, take a second and just think back, because for anyone over the age of 30, the ozone hole was, um, it was very likely the defining environmental terror of your entire childhood.
Absolutely. It was everywhere.
It was absolutely everywhere. We were constantly bombarded with these apocalyptic warnings about deadly UV rays. People were genuinely terrified to go outside without thick layers of sunscreen.
And there was all that guilt, too.
Yes, this overwhelming everyday guilt associated with something as simple as using a can of aerosol hairspray or bug spray. But here's the crazy part. If you ask anyone in their 20s or younger about the ozone hole today, you will probably just get a blank stare.
It's true. They have no idea.
It is practically unheard of for an entire generation.
It really is a fascinating phenomenon in human psychology and global media. I mean, it is as if this apocalyptic threat just dropped off the face of the earth.
Yeah.
And it naturally makes you wonder, did the hole just magically vanish? Did we all just collectively imagine the danger? Or did we simply stop talking about it because the news cycle inevitably moved on to the next big crisis?
And that is exactly the mystery we're unpacking today. In this deep dive, we are going on a mission to completely deconstruct the terrifying science, the incredibly dramatic history, and ultimately the triumph of the ozone layer crisis.
It's quite a story.
It really is. We want to figure out what ozone actually is, how a so-called miracle invention of the 20th century almost literally sterilized the surface of the Earth, and how humanity managed to pull off what might be its greatest, most unified rescue mission in history.
And we need to establish right up front that this isn't just some dusty, resolved history lesson. It is a profound case study. The timeline of the ozone crisis reveals a story of how pure critical thinking and basic scientific curiosity literally saved all terrestrial life on Earth.
No exaggeration.
None at all. It is a blueprint, and perhaps the only truly successful blueprint we currently have for how humanity can actually handle massive, self-inflicted global crises today.
Okay, let's unpack this. Because before we get to the impending doom, we need to understand the protagonist, or rather the shield, of our story.
Right.
Most of us have heard the word ozone, but what actually is it? We all know that the oxygen we breathe every second to stay alive is O2, but the addition of that third oxygen isotope to create O3 completely radicalizes the molecule's behavior.
It really does.
It goes from a highly stable, inert, life-giving gas to something entirely different.
What's fascinating here is just how aggressively that third atom alters the physical properties of the gas. For instance, the O2 we breathe is completely colorless and odorless, but pure ozone, O3, is actually a pale blue color at room temperature.
Pale blue, that's so weird to think about.
Right. We almost never encounter pure ozone in our daily lives, so very few people know about the color. But it also possesses a very distinct, sharp, almost electric odor.
I always think of that smell right after a massive, violent thunderstorm. You know, that incredibly crisp, fresh scent in the air right after a close lightning strike?
Yes, exactly.
That is literally ozone. The immense electrical energy of the lightning shatters the O2 molecules in the air, and they recombine into O3.
And in those tiny localized doses, it smells incredibly fresh.
Right, but in large doses, it absolutely stinks. I mean, the word ozone itself actually derives from the Greek word ozi, which translates to smell.
It's a fitting name for a gas with such an extreme Jekyll and Hyde dual nature. Its impact on biological life depends entirely on where it is located in the atmospheric column.
Okay, let's break that down.
Let's start with the darker side of that duality. About 10% of all naturally occurring ozone exists right down here at ground level in the troposphere. And down here, ozone is a highly reactive toxic pollutant.
So it's bad news down here.
Very bad news. It aggressively oxidizes lung tissue, it is severely harmful to animals, and it damages plant biology. It is not something you want in your immediate environment.
But then you look up. The remaining 90% of the Earth's ozone is located way, way above us in the stratosphere. We're talking roughly 15 to 30 kilometers above the surface.
That's incredibly high up.
To put that into perspective, commercial jets cruise at an altitude of about 10 kilometers. So this massive reservoir is sitting far higher than our planes even fly.
Right.
Up there, safely away from our lungs, it stops being a localized toxin and instead acts as Earth's ultimate spacesuit.
Although, describing it as a massive reservoir can lead to a bit of a misconception.
How so?
Well, when you look at the raw atmospheric data, the total amount of ozone in the atmosphere is roughly 3 billion tons.
Which sounds huge.
It sounds like an unimaginably heavy amount of gas.
Yeah.
The Earth's atmosphere is so vast, so incredibly voluminous, that this 3 billion tons only makes up about 0.0006% of the atmosphere's total mass.
Wait, hold on. Let me just visualize that. 0.0006%. That is barely a statistical rounding error.
Precisely. It is an unimaginably thin, fragile layer. If you were to bring all of that stratospheric ozone down to sea level and compress it to standard atmospheric pressure,
Okay.
the entire ozone layer, the only thing protecting our entire planet, would be just a few millimeters thick.
Are you serious?
Yes. Think about the thickness of 2 pennies stacked together. That is the razor-thin biological shield standing between a vibrant, living Earth and absolute sterilized devastation.
Just 2 pennies. That is terrifying. Which brings us to the actual threat, because we all love a sunny day, but the sun is essentially a giant nuclear furnace constantly blasting us with ultraviolet, or UV, radiation.
It is.
And we need to break down the spectrum of this UV light into 3 distinct categories to really understand why they matter to your biology, right down to the cellular level.
You can categorize them by their energy levels and wavelengths. Let's start with UVA. This is the least directly harmful of the 3, and it is the one that mostly reaches the surface of the Earth.
Because the ozone layer lets it through, right?
Yeah, exactly. The ozone layer barely absorbs any UVA. When you go outside and get a tan or experience certain sun-related skin aging, that is almost entirely the work of UVA rays. It penetrates deep into the skin, but it generally doesn't possess the sheer energetic force to cause immediate, catastrophic cellular damage.
Okay, so that's the baseline. Then we step up the danger ladder to UVB. This is medium harm.
Yes.
This is the stuff that causes severe sunburns, but more importantly, it causes skin cancer. It also actively suppresses the human immune system, meaning your body loses its ability to fight off viruses and bacterial pathogens.
Which a lot of people don't realize.
Right, and it is the primary culprit behind cataracts in our eyes. If the ozone layer weakens, UVB is the immediate threat that starts leaking through in higher doses.
And then finally we have UVC. This is the ultimate killer.
The bad one.
The worst. UVC radiation is so incredibly energetic and so violently destructive that it doesn't just burn tissue, it directly strikes and shatters DNA molecules.
It literally breaks the DNA.
It breaks apart the foundational genetic code of living cells. If UVC were allowed to freely reach the surface of the Earth, almost all terrestrial life would simply be wiped out. Carbon-based life forms, as we know them, cannot survive sustained UVC exposure. It is a sterilizing force.
And the data on what happens when that fragile 0.006% shield gets even slightly compromised is chilling. A mere 10% reduction in the ozone layer doesn't just mean a few more uncomfortable sunburns at the beach.
Not at all.
A 10% drop leads directly to a 26% increase in malignant skin cancer rates globally. Furthermore, it triggers a 0.6 to 0.8% increase in global cataracts.
Which, when applied to a global population, translates to 10,000 to 15,000 additional cases of irreversible blindness every single year.
Wow.
And the devastation is by no means limited to human biology or terrestrial land masses. UVB radiation has the energy to penetrate the surface of the ocean. When it does, it directly kills phytoplankton and other microscopic marine algae.
And if you kill the phytoplankton, you essentially pull the linchpin out of the entire marine food chain.
Precisely.
If they die, the krill and shrimp die. If they die, the small fish die, then the larger predators. The entire oceanic ecosystem collapses from the absolute bottom up, just from a slight sustained increase in UVB radiation.
But what's fascinating here is the mechanism the ozone shield uses to stop this radiation. It's remarkably elegant. It isn't just a static physical wall that blocks light like a piece of lead. It is an active, dynamic chemical engine.
How does it work?
When lethal UV light from the sun hits an ozone molecule, the O3 actively absorbs that deadly energy. In doing so, it converts the destructive radiation into completely harmless infrared heat.
But absorbing that massive hit of nuclear energy shatters the ozone molecule.
It does, but only temporarily. The impact of the UV energy breaks the O3 apart, splitting it into a standard oxygen molecule, O2, and one free-floating, highly reactive oxygen atom.
Okay.
But in the chaotic, pressurized environment of the stratosphere, that O2 and that free O naturally and almost immediately recombine back into O3.
So it takes the hit, shatters into pieces, and then immediately glues itself back together, ready to take another hit.
Exactly.
It is a perfect, infinite loop of breaking and reforming, a completely self-sustaining shield that never actually gets permanently depleted by the sun.
Left to its own natural equilibrium, It is a perfectly balanced biological defense mechanism that has protected Earth for hundreds of millions of years.
Right.
But about a century ago, human industrial progress introduced a synthetic variable that the atmospheric chemistry was entirely unprepared for.
And it all started because we were trying to solve a completely unrelated problem down on the ground, didn't it? Keeping our food cold.
Yes. Let's travel back down to Earth, specifically to the early 20th century, and look at the refrigeration crisis. Because before the 1920s and 30s, if you wanted to keep things cold,
Whether it was a commercial meat warehouse or an early attempt at air conditioning.
the chemical refrigerants available were absolute nightmares. They relied on substances like ammonia and sulfur dioxide.
These were essentially industrial poisons. They were highly toxic, highly flammable, and incredibly corrosive to the pipes that contained them.
The risk to the average consumer was profound. If you had an early primitive refrigerator in your home and a simple pipe leaked in the middle of the night, it wasn't just a matter of your milk spoiling.
Yeah.
A leak of ammonia or sulfur dioxide gas into a poorly ventilated home was a literal death sentence for the family sleeping inside.
Yeah.
The sheer danger was a massive barrier to the widespread adoption of modern cooling technologies.
So the world desperately needed a solution, a refrigerant that was safe, chemically stable, and wouldn't kill you if the compressor had a tiny leak. Enter Thomas Midgley Jr., a brilliant American chemist.
He was tasked with solving this exact engineering bottleneck.
And he delivered what was universally considered at the time to be an absolute industrial miracle. He invented a class of chemicals called chlorofluorocarbons, or CFCs, but the world came to know them by their most prominent commercial brand name, Freon.
Looking at it strictly from a 1920s engineering perspective, Freon was hailed as the perfect chemical. It was incredibly stable, meaning it didn't aggressively react with other chemicals or corrode machinery. It was entirely non-toxic to breathe in normal amounts. It was completely non-flammable. It had no odor. And crucially for the thermodynamics of refrigeration, it could be compressed into a liquid and expanded back into a gas very easily with minimal energy.
Because it solved every single problem the industry had, Freon completely exploded into everyday life. It wasn't just pumped into every single refrigerator and air conditioner across the globe. Industry started finding a million other uses for it.
Oh, absolutely.
They used it to manufacture foam plastics. They used it heavily as a precision cleaning agent for delicate electronics and aerospace circuit boards because it was non-conductive, evaporated instantly, and wouldn't dissolve in water.
And perhaps most visibly to the average consumer, it became the driving force behind the aerosol spray revolution.
The spray cans.
Because Freon could easily be compressed into a liquid inside a tiny metal can and then rapidly expand into a gas when the pressure was released by a nozzle, it was the perfect chemical propellant. Almost every single spray can in the world, hairspray, bug spray, spray paint, deodorants, asthma inhalers, was powered by Freon.
I have to share this wild historical anecdote about the sheer PR muscle that went into convincing the world that Freon was a benevolent miracle.
Oh, the press conference.
Yes. To calm any lingering public fears about chemical refrigerants after the trauma of the ammonia days, Thomas Midgley Jr. held a massive, highly publicized press conference. While reporters and photographers watched, he literally inhaled a deep lungful of pure Freon gas, held it in, and then gently exhaled it directly onto a lit candle, blowing the flame out.
It's hard to imagine someone doing that today.
In one single theatrical stunt, he proved to the world that Freon was completely non-toxic to breathe and entirely non-flammable.
It was undeniably a marketing masterpiece. However, hindsight reveals a much darker reality. While Freon was celebrated as perfectly safe for short-term exposure, it wasn't a completely benign substance, even to humans.
Right, there were hidden dangers.
Massive long-term exposure, the kind experienced by industrial workers constantly servicing air conditioners over decades, carry severe risks of neurological damage and heavy organ damage, particularly to the liver and kidneys.
Which they just didn't study at the time.
Exactly. Furthermore, if Freon is subjected to extremely high temperatures, it undergoes a radical chemical change and produces phosgene gas.
Phosgene gas, that was literally used as a highly toxic, lethal chemical weapon in the trenches of World War I.
Yes, so while stable at room temperature, it harbored some terrifying latent properties.
But for 40 years, from the 1930s all the way into the 1970s, nobody knew, and quite frankly, nobody cared. We just kept pumping thousands and hundreds of thousands of tons of Freon into the air every single day.
Without a second thought.
Every time someone sprayed their hair for a night out, every time an old fridge was scrapped in a junkyard, that freon vented directly into the atmosphere. And because it was invisible and didn't make anyone immediately sick, we operated under the assumption that it just harmlessly dissipated into the void.
This raises an important question, and it is the exact question that eventually changed the course of human history. If a chemical is perfectly stable, meaning it never reacts with anything in the soil, it doesn't dissolve in the ocean, and it never breaks down in the lower atmosphere,
Where does it go?
where does it actually go after you spray it out of a can? It has to
Ah.
go somewhere.
Here's where it gets really interesting. In 1973, we meet the unlikely detectives of our story. A Mexican chemist named Mario Molina, who was a postdoctoral researcher in the United States at the time, and his academic advisor, Frank Sherwood Rowland.
Two crucial figures.
What's vital to understand is that they weren't environmental activists looking to take down a massive chemical corporation. They were just two scientists driven by pure, unadulterated curiosity. They looked at the massive global industrial output of Freon and simply wanted to answer that one fundamental question. Where does the indestructible gas end up?
What they discovered through their meticulous calculations was a terrifying hypothesis. Because Freon doesn't break down at ground level, it just accumulates. But the Earth's atmosphere is not a static room. It is a highly dynamic system of convection and air currents.
It mixes.
Over decades, these indestructible Freon molecules slowly, steadily drift upward, and eventually they reach the stratosphere.
And what sits waiting in the stratosphere? The ozone layer. Molina and Rowland theorized that once the Freon got high enough to escape the protective umbrella of the ozone layer, the intense, unfiltered UV light from the sun would finally do what nothing on Earth could do.
It would shatter the perfect Freon molecule.
Yes. And the chemical pieces left behind would violently react with and destroy the ozone. Realizing the entire planet was in grave danger, they quickly published a paper detailing their findings and warning the scientific community.
The reaction from the multi-billion-dollar chemical industry was swift, brutal, and entirely predictable. Manufacturers of CFCs, led by massive chemical giants like DuPont, launched a ferocious public relations and lobbying campaign to entirely discredit Molina and Rowland.
They really went after them.
They dismissed their peer-reviewed research as scientific fantasy and fear-mongering nonsense.
The industry's main technical argument was that Freon molecules were simply too heavy, too dense to ever float all the way up to the stratosphere. They argued it would just settle near the ground or get trapped in the lower troposphere.
Which sounds plausible if you don't do the math.
Right. And even if it did somehow miraculously float up there against the pull of gravity, they claimed it was far too stable a compound to ever cause the kind of catastrophic runaway atmospheric harm Molina and Rowland were modeling.
But Molina and Rowland refused to be silenced by corporate intimidation. They understood the physics, and they knew they needed irrefutable physical proof. They spent 3 relentless years fighting the industry narrative.
Doing the hard work.
They moved out of the theoretical realm of laboratory calculations and started launching high-altitude weather balloons equipped with sophisticated atmospheric sampling equipment directly into the stratosphere.
And what did those balloons capture? Hard, undeniable physical reality. They found massive, undeniable concentrations of Freon high up in the stratosphere, sitting right in the heart of the ozone layer.
They proved the multi-billion-dollar industry entirely wrong. The heavy gas was drifting up.
By 1976, their unyielding dedication paid off. The highly respected United States National Academy of Sciences conducted an independent, rigorous review of their balloon data and their atmospheric chemistry models, and they officially validated their work.
A huge turning point.
They confirmed that CFCs were a legitimate existential threat to the ozone layer. This discovery was so monumental, so vital to the survival of the planet, that nearly 20 years later, in 1995, Molina and Rowland were awarded the Nobel Prize in Chemistry.
But to truly appreciate what they saved us from, we have to look closely at the precise mechanics of the destruction they uncovered. This isn't a simple one-to-one case of one Freon molecule knocking out one ozone molecule. If it were, the threat would be manageable.
Right, it's much worse.
The chemistry involved is terrifyingly efficient. It revolves around a specific elemental component of Freon, chlorine.
I've heard chlorine described in atmospheric chemistry papers as a kind of serial killer atom. What makes it so uniquely destructive once it gets knocked loose up there?
Let's walk through the exact catalytic cycle. When that Freon molecule finally drifts up above the ozone layer, it gets hit by the full, unfiltered force of the sun's UV rays. Freon is incredibly stable, but it's not invincible against nuclear radiation.
The UV just blasts it.
The intense UV energy finally snaps the strong chemical bonds of the Freon molecule. When it snaps, it ejects a free chlorine radical, a highly reactive, unstable chlorine atom.
And this free chlorine atom is the serial killer. Once free, it violently attacks a nearby ozone molecule, our beneficial O3. It forcefully steals one of the oxygen atoms away.
Exactly.
This transforms the ozone back into regular, non-protective oxygen gas, O2, and creates a new molecule called chlorine monoxide. So far, one ozone molecule is dead, and the biological shield is weakened. But the horror show is just beginning.
Because the process doesn't stop there. The stratosphere is full of free-floating single oxygen atoms generated by the normal UV absorption process we discussed earlier.
Right.
When one of these free oxygen atoms comes along and bumps into the chlorine monoxide, it grabs the oxygen atom from it to form another O2. And in doing so, it aggressively kicks the chlorine atom loose again. The chlorine is completely freed.
Freed to kill again. It loops right back, finds another unsuspecting ozone molecule, violently steals an atom, gets knocked loose by another free oxygen atom, and repeats the process again and again and again.
The math here is staggering. Because it is a catalytic chain reaction, the chlorine atom is never actually consumed in the process. A single chlorine atom released from a single Freon molecule can systematically hunt down and destroy hundreds of thousands of individual ozone molecules before it eventually reacts with something else and naturally cycles out of the stratosphere.
Hundreds of thousands.
We weren't just throwing rocks at our planetary shield. We were unleashing millions of microscopic, endlessly recycling buzzsaws into a fragile web.
This mathematical reality of the chain reaction was alarming to scientists in the 1970s, but to the general public and politicians, it was still somewhat abstract. It was a theoretical model on a chalkboard.
It was hard for people to visualize.
That all changed in 1985. That was the year the theoretical threat became a highly visible, globally terrifying reality. The British Antarctic Survey, a team of researchers stationed in the most remote, desolate part of the world, was taking routine measurements of the atmospheric column over Antarctica, and what they discovered was completely unprecedented in the history of atmospheric science.
During the Antarctic polar spring, which happens around September and October as the southern hemisphere warms, they measured the stratospheric ozone levels. They found that they hadn't just dipped slightly or thinned out, they had absolutely plummeted.
Plummeted.
The ozone concentration over the entire massive continent of Antarctica had dropped by a staggering 60%. It wasn't a gradual thinning, it was an absolute structural collapse. It was a gaping hole in the sky.
Which immediately begs the question, why Antarctica? Why did the hole appear over the most isolated, freezing, completely unpopulated continent on Earth, thousands of miles away from all the hairspray, air conditioners, and industrial factories in North America and Europe?
It seems counterintuitive, but the answer lies in the highly specific, extreme chemical conditions required for this chlorine slaughter to accelerate to such catastrophic extremes. The atmospheric physics over the South Pole create a unique environment.
Right. It turns out the chlorine chain reaction we just talked about acts like it is on steroids when it is subjected to two very specific conditions: extreme, intense cold, and a sudden influx of bright sunlight.
And Antarctica has both.
Antarctica obviously has the cold in abundance. During its brutal, months-long winter night, the atmosphere forms something called a polar vortex. As the Freon drifted globally, it got sucked into this vortex over the pole. The extreme cold allowed massive amounts of these reactive chlorine chemicals to build up and freeze into high-altitude polar stratospheric clouds.
They gathered in these massive frozen clouds, but they lay completely dormant in the absolute darkness of the polar night. The chemical trap was set, loaded with millions of tons of reactive chlorine, but it desperately needed a trigger.
What's up?
And that trigger is the sunrise. When the long, dark polar winter finally ends and the sun peaks over the Antarctic horizon in September, the sudden flood of energetic UV light hits that massive, concentrated buildup of Freon and frozen chlorine, all at exactly the same time.
The perfect storm.
The resulting reaction is violent, explosive, and exponentially faster than anywhere else on Earth. In a matter of weeks, the sudden catalytic chain reaction literally tears a gaping hole straight through the ozone layer.
What blows my mind about this discovery is how NASA reacted. When the British team published their findings about this catastrophic 60% drop, the scientists at NASA were completely baffled. NASA had their own fleet of highly advanced weather satellites continuously monitoring the global atmosphere.
Right, so why didn't they see it?
Exactly.
Yeah.
They rushed to check their satellite data, asking themselves, how on earth did a multi-billion-dollar space agency miss a hole the size of a continent?
What they found when they dug into their systems is a deeply sobering lesson in the philosophy of data collection and the limits of automation. Why do we program algorithms to ignore massive outliers? Because 99.9% of the time, a massive outlier is a sensor glitch.
So the computer just tossed it.
It turns out NASA satellites had indeed recorded the massive ozone hole. The orbital sensors had accurately detected the catastrophic drop in ozone levels. But the data they fed back to the ground stations was so extreme, and the numbers were so unbelievably, impossibly low, that the automated processing software assumed the satellite's physical sensors must be broken.
That is wild.
The computer algorithm literally flagged the atmospheric apocalypse as a hardware error and automatically deleted the data to keep the database clean.
It wasn't until the human scientists went back, bypassed the algorithms, and manually reviewed the raw, unfiltered data that they confirmed the absolute nightmare. There was indeed a monstrous, undeniable hole ripped into the atmosphere directly above the South Pole.
The visual confirmation of this hole shifted the paradigm entirely. It moved the issue from the abstract realm of atmospheric chemistry to an immediate, visceral, highly visual global crisis. And there was a brilliant piece of science communication that happened at this exact juncture.
Yes.
The scientific community and the media made a very deliberate, highly effective choice in how they named the phenomena.
Oh, this is so crucial. They could have been strictly academically accurate and called it an Antarctic stratospheric ozone depletion zone, but nobody's going to march in the streets or call their congressman over a depletion zone.
Exactly.
Instead, they called it the ozone hole. That single, highly evocative word choice changed everything. A hole is something anyone can understand. A hole sounds like something is broken, something is leaking, something needs to be urgently plugged and fixed before everything inside dies. That phrasing bypassed the intellectual centers of the brain and sparked genuine, primal, global terror. People demanded immediate action.
And that intense public demand led to one of the most remarkable and unlikely political shifts in modern history. The global response wasn't driven merely by environmental activists or Green Party politicians. It was championed by some incredibly unlikely political figures. Specifically, the global push was spearheaded by United States President Ronald Reagan and United Kingdom Prime Minister Margaret Thatcher.
Regardless of where anyone sits on the political spectrum or what you think of their wider geopolitical ideologies, their specific personal backgrounds were the exact catalysts needed for this specific crisis. Ronald Reagan had personally battled severe skin cancer. He had literal pieces of skin removed from his nose.
Because of that traumatic personal experience, he was highly sensitive to the medical threat of increased UV radiation. He understood the biological stakes on a deeply personal, non-abstract level.
And Margaret Thatcher brought a completely different but equally vital perspective to the table. Before she entered politics, Thatcher actually held a degree in chemistry and had worked professionally as a research chemist.
She knew her stuff.
She didn't need advisors to water down the science for her or translate complex reports into bullet points. She could sit down, read Molina and Rowland's original peer-reviewed papers, look at the satellite data, and completely understand the terrifying mechanics of the chlorine chain reaction herself. She recognized the undeniable scientific reality of the threat without needing it filtered through a political lens.
With the backing of these major global powers, the world actually got together to do something about it. In September 1987, delegates from 24 nations, along with the European Economic Community, gathered in Montreal, Canada. They sat down and negotiated what would become known as the Montreal Protocol.
A huge moment.
The goal was massive, economically terrifying, and completely unprecedented, to completely phase out the global production and consumption of all CFCs.
But we have to look deeper into why this treaty succeeded where so many other environmental initiatives fail. It wasn't just a sudden global moral awakening. Environmental progress almost always requires economic realities to align with scientific warnings.
The money has to make sense.
Right. For one, the major chemical companies like DuPont were looking at their balance sheets. Their lucrative patents on Freon and other early CFCs were beginning to expire. However, they already held the patents for the next generation of replacement chemicals. Banning Freon was no longer a total economic death sentence for them. It was a state-mandated transition to their new, highly profitable, patented products.
That economic incentive is a huge piece of the puzzle. But the treaty itself was also brilliantly designed from a geopolitical standpoint. The negotiators understood that instantly banning cheap, reliable refrigerants globally would economically devastate developing nations that relied heavily on them for basic infrastructure, medicine storage, and food preservation.
So they made it flexible.
So they built a highly pragmatic fairness directly into the policy. The treaty required the wealthy, heavily industrialized nations like the United States, the European countries, and Japan to completely halt their production of CFCs by the year 1996. They possessed the massive wealth, the infrastructure, and the technological capacity to pivot to more expensive chemical alternatives quickly.
But for developing nations, including massive, rapidly industrializing economies like China, India, and Brazil, the treaty provided a critical grace period. They were given until the year 2010 to completely phase out Freon.
Smart move.
This allowed them time to develop their economies without being entirely crippled by the sudden loss of vital cooling technologies, while still legally committing them to the ultimate global environmental goal.
And the most incredible part of this tiered approach, it worked better than anyone could have realistically modeled. Many developing nations actually completely blew past their deadlines in the best way possible.
They finished early.
China, which joined the protocol in 1991, aggressively phased out the chemicals and completely ceased production of CFCs in July 2007, a full 2.5 years earlier than their mandated deadline. India completely ceased their production by the middle of 2008. The developing world stepped up massively, recognizing the existential nature of the threat.
If we connect this to the bigger picture, the sheer scale of what the Montreal Protocol achieved is breathtaking. This is a staggering historical fact that often gets overlooked. The Montreal Protocol is the only treaty in the entire history of the United Nations to achieve universal ratification.
Every single one.
Every single recognized country on the face of the earth signed on and agreed to its terms. It is unanimously considered to be the single most successful international environmental agreement humanity has ever created.
But of course, nature operates on its own timeline, and it doesn't fix itself overnight just because politicians sign a piece of paper. Which naturally leads to a lingering question you might be having right now. If we all got together, held hands, and aggressively banned Freon back in the late 1980s and 1990s, why did we keep hearing news reports about the ozone hole getting bigger and worse throughout the late 90s and into the early 2000s? Why didn't the ban immediately stop the bleeding?
That is a critical point, and it comes right back to the slow, relentless physics of the atmospheric convection we talked about earlier. Remember the time lag? It takes decades for Freon released at ground level to slowly drift all the way up into the stratosphere.
It takes a long time.
So the horrific chemical slaughter we witnessed over Antarctica in the 1980s and 90s wasn't caused by the hairspray someone used in 1985. The hole that panicked the world was entirely caused by the millions of tons of CFCs that were pumped out during the massive industrial booms of the 1930s, 40s, 50s, and 60s.
It was quite literally a ghost from the past haunting the sky. Even though we slammed the brakes on new global production in 1987, there were still millions of tons of Freon slowly floating upward through the troposphere, acting like a massive chemical time bomb that hadn't detonated yet.
So it kept getting worse.
Because of this massive multi-decade delay, the Antarctic ozone hole actually continued to grow and expand for over a decade after the ban was universally implemented. It officially peaked in size around the year 2000.
Let me stop you for a second, because the scale of that peak is horrifying and hard to visualize. At its absolute largest, around the turn of the millennium, the hole reached nearly 30 million square kilometers. To put that abstract number into perspective, 30 million square kilometers is large enough to comfortably fit the entire continent of North America inside it.
That is massive.
Alternatively, you could take the entire combined land masses of both Russia and China and drop them into that single void in our atmospheric shield.
And this massive void wasn't just hovering safely over unpopulated Antarctic ice. As the hole expanded, its thinned-out edges stretched dangerously far north. It reached directly over highly populated areas like southern Australia, New Zealand, and the southern tip of Chile. The millions of people living under that compromised shield were subjected to intense, unfiltered UVB radiation every time they stepped outside.
The direct biological consequence of that geographical shift was severe. Skin cancer rates in Australia absolutely skyrocketed, eventually becoming the highest in the entire world. They literally had to change how their entire society interacted with the sun. It changed public health campaigns, school uniforms, and outdoor culture permanently.
While the world nervously waited for the old Freon to finally burn itself out in the stratosphere, the chemical industry was frantically trying to figure out what to put in our air conditioners and refrigerators instead. Finding a safe, effective, and economically viable substitute for the miracle chemical has been incredibly difficult. And to be entirely honest, it is an ongoing struggle today.
It wasn't an easy fix.
The initial replacements we rushed out to replace CFCs were a class of chemicals called HCFCs.
Right, HCFCs. They were technically a step in the right direction because they broke down faster and were significantly less destructive to the stratospheric ozone layer than Freon. But they had a massive hidden flaw that we didn't fully appreciate at the time.
We traded one problem for another.
It turned out that while they were saving the ozone, they were acting as incredibly potent greenhouse gases, vastly accelerating global warming. We essentially traded one localized atmospheric apocalypse for a slower global heating one. So the international community had to gather again and aggressively phase those out too.
Which led the industry to the next generation of synthetic refrigerants, HFCs. Now, HFCs are entirely ozone safe, meaning they do not contain that serial killer chlorine atom at all, and their greenhouse gas effect is considerably lower than their predecessors.
But there's a catch.
However, there is a deeply concerning new issue emerging. When HFCs are released and react with the open air, they break down over time to create a persistent substance called trifluoroacetic acid, or TFA.
And here's the terrifying, almost cyclical parallel to the start of our story. The long-term environmental and biological impact of large amounts of TFA raining down and accumulating in our freshwater lakes, rivers, and soil is currently almost entirely unknown.
We don't know what it does long term.
We are essentially flying blind again, echoing the exact same technological hubris we had in the 1920s when we first assumed Freon was perfectly harmless because it didn't kill us immediately. We are, right now, releasing a highly stable, man-made chemical into the global environment without knowing the ultimate multi-generational consequences.
It is a profound, sobering reminder of the limits of our scientific foresight. In fact, the struggle to engineer a perfectly safe, universally effective synthetic chemical is so fraught with unintended consequences that, ironically, a significant portion of modern industrial refrigeration is actually reverting back to the very chemicals Thomas Midgley tried to replace 100 years ago. Many massive, large-scale industrial cooling facilities, data centers, and meatpacking plants are now going back to basics and using ammonia.
Wait, the highly toxic explosive ammonia that literally killed families in their sleep in the 1920s?
The very same. But the critical difference is that a century of technological advancement has fundamentally changed how we handle it. We now possess highly advanced computerized leak sensors, automated safety shutoff valves, incredibly durable alloys, and superior industrial safety management.
So we can use it safely now.
We can utilize ammonia's incredibly efficient cooling properties while effectively mitigating the explosion and toxicity risks through rigorous modern engineering. The industry essentially decided that it is safer to manage a known, localized physical danger than to endlessly release unknown, potentially world-ending miracle chemicals into the global sky.
Okay, despite the ongoing, very real engineering challenges with replacements, I want to pivot back to the truly incredible, highly optimistic good news. Because of the Montreal Protocol, because every single country in the world actually followed through, sacrificed short-term economic gains, and completely stopped producing Freon, the global crisis has genuinely been averted.
It really has.
We finally stopped feeding new chlorine into the chain reaction, and the atmosphere's perfect biological loop is working again. The ozone layer is naturally, steadily healing itself.
The long-term projections for recovery are highly optimistic and represent what is arguably the most monumental victory for global environmental policy in human history. Based on current, highly rigorous scientific monitoring from satellites and ground stations, the overall global ozone levels are projected to fully return to their healthy, pre-crisis 1980 benchmarks by the year 2040.
That's not that far away.
And the Arctic ozone layer, which also suffered significant depletion, is expected to heal entirely by 2045.
And the massive, terrifying hole over Antarctica, the one that could fit all of North America, even that catastrophic continent-sized wound is slowly closing. Current atmosphere projections show the Antarctic hole will be completely and permanently healed by the year 2066.
We will see it close in our lifetimes.
We are literally watching the Earth repair the devastating damage we caused in real time because we actually stepped back and let it.
It is a stunning testament to the incredible resilience of our planet's natural systems, provided we simply give them the opportunity to recover. by removing the artificial disruptive catalysts we introduce.
When you step back and look at this entire century-long journey, you have to marvel at the sheer terrifying luck of the situation. If Mario Molina hadn't been driven by pure academic scientific curiosity to ask a simple, seemingly unimportant question about where a harmless gas goes,
If he hadn't asked.
if he hadn't possessed the immense tenacity to launch those weather balloons and fight a multi-billion-dollar PR war against the most powerful chemical companies on Earth, we might not have realized what was happening until it was far too late. Humanity might have been entirely sterilized by UV radiation before we even understood the chemical mechanics of our own destruction.
It was an incredibly near miss for our entire species. We engineered a brilliant, profitable tool that almost unmade us, and we were ultimately saved by the very rigorous scientific method that created the tool in the first place.
So what does this all mean? For me, the ozone crisis is the ultimate, undeniable proof that humanity can unite to solve a massive, self-inflicted existential threat. We didn't just throw up our hands in despair and accept our fate. We didn't just resign ourselves to living underground or wearing radiation suits for the rest of human history.
We fixed it.
We saw a global problem. We actively and radically changed our global economic behavior. We entirely restructured multi-billion-dollar industries, and we literally saved our planet. It is the absolute greatest success story we have.
The story of Freon is a story of a miracle technology that solved an immediate problem while silently creating an apocalyptic one decades down the line. It took a curious mind looking up at the sky to save us. As you look around at the miracle materials and conveniences filling your life today, you have to wonder, what invisible threat are we currently unleashing right now, just waiting for the next Mario Molina to discover it before it's too late?